We're going to be talking about introducing the concept of sampling distributions. So here's the roadmap. We've been talking about probability distributions, and that's what we call probability distributions of probabilities from discrete outcomes. But now we're going on to sampling distributions, and that's what we call distributions of outcomes that are continuous. For now, we could apply the same fundamental logic from probability distributions directly to sampling distributions. We could treat them roughly similarly. But I do want to connect sampling and research methods, two topics we've covered before, with sampling distributions. And then we're going to finally talk about actually generating sampling distributions. Okay, so first let's talk about the difference between probability and sampling distributions. So in probability distributions, we're always looking at discrete outcomes, finite or countable numbers of outcomes. So for example, in binomial distributions, if you have 10 trials, you have 0 to 10 different outcomes as possibilities, right? So that's 11, right? They're discrete, they're finite, they're countable, no problem. And those in probability distributions, what we're looking for is the probabilities of those discrete outcomes, right? So we get a list of all these probabilities. And we could actually make a list because it's a finite number. Okay, now that we know that, now let's talk about sampling distributions. Sampling distributions are roughly the same idea. You have this sample space, and you want to know how likely each outcome is, the probability of each outcome, and the set of all those probabilities, that's called a sampling distribution. But here's the big difference. Instead of discrete outcomes, now we're talking about continuous outcomes. Right? So before we asked, what's the probability that 2 out of 4 random people that you pick from the United States will have a bachelor's degree. Now we might say if you pick 2 out of 4, if you picked 4 college students at random, we're not looking for the 2 anymore. That's discrete, right? We're looking for things like what is their average GPA. Right? There's an infinite number of average GPAs that you could potentially have, right? So in that way, it's not finite anymore, but it's infinite number of outcomes, and uncountable number of outcomes. Now, that is problematic for us because here we had like a list of all the different probabilities. Can you list all these outcomes? No, that's impossible. They're infinite, right? So it's by definition not listable, not put in a table-able, right? And so that's an issue with sampling distributions. But sampling distributions get their power from other sources. So we don't have to worry as much about that. But I do want you to know that this is the big difference between probability distributions and sampling distributions. But still, we're going to be trying to find things like, how do we find the expected value of these distributions? How do we find the probability of some outcome, All right. But the same overall logic is going to apply for now. And so I want to just go over the logic of the original probability distributions. All right. So basically, we use probability to find, so this is, let's say, a known population, right? So we had known populations like things like fair coins, the roll of 2 fair die, I don't know, whatever, something like that. And from that, we generate a probability distribution. So a whole bunch of different values for this random variable x, right? And then the probabilities of those x's. Okay. Once we have that, then we have this sample from here. Sample, and it's actually from an unknown population. So we get the sample and we're like, is it good? You know, is it from this kind of population? Is it from that kind of population? We don't know, right? What we do is we take the sample and we compare it to the probability distribution. And we look at, is this sample very likely? Is it very unlikely, right? And from that, we judge whether this known and unknown population is similar to each other or not, right? Is it likely, unlikely, right? So that's roughly that idea. Now, we went over a couple of specific examples. One of the ones that we went over in great detail was the one with 2 die, where the random variable is the sum of the 2 die, right? So that's an example. The logic of sampling distribution is roughly similar. So we have some known population. We generate a sampling distribution this time instead of a probability distribution. And we'll talk about how to generate those later. We get samples from unknown populations and we compare it and we say, oh, is it likely? Is it unlikely? So same underlying logic. The differences are going to be in this step. How we generate is going to be different, right? And how we judge whether it's likely or unlikely, this step is also going to be a little bit different in terms of the nitty-gritty, like how we actually do it. But the concept is the same. We have this known stuff, we have this unknown stuff. We compare the unknown stuff to the known stuff. Ta-da! Okay, but let's go over that example that we knew really well. So the known let me use black here. So the known population here was 2 fair die, right? 2 fair die that we rolled, right? And we generated this probability distribution. So here we have the probability distribution. And this is a probability distribution where x, the random variable, is the sum of 2 die, right? And we also generated all these probabilities for each sum, right? So we have the sum of the 2 die, we have all the probabilities for each of those sums, right? And each of these sums is discrete and countable. There's 10, 11 of them, right? Ta-da! All right. Now, what we would do is, let's say we rolled 2 die, and we don't know if they're fair die or not. We don't know. Some shady guy gave it to us, right? We want to know, is this a fair die or not? Well, if we got a roll such as 1-1, right? If that's what our sample was, then we could say, okay, what is the probability that x equals 2? Well, that's a pretty small probability. It looks like 0.025 or something, right? So because it's a small probability, we'll say this is unlikely. This is an unlikely sample, right? But let's say we got a sample that was something like 3, 4, right? And so we might compare that to this probability where x equals 7, right? And that is pretty likely. There's like, I don't know, say 16% chance, right? And so we would say, oh, this is likely, right? So this sample, we would probably say, oh, if we got this, we would say, oh, it's pretty likely that it came from fair die. If we got this sample, we might say, oh, it's less likely, right? It's not that we stop here and say, oh, these die are unfair, because there is still a chance that you could get this, but it's just less likely, and this is just more likely. So we're judging them relative to each other. All right. Now, we're going to do something similar, but some of these steps will differ, namely this one and this one. Okay. So how do we get a sample sampling distribution, right? We know how to get probability distributions. Probability distributions are really straightforward because we use those fundamental rules of probability. Sampling distributions are different. We can't use those probability rules necessarily. So before, what we did in probability distributions was we used things like the law of large numbers, and we could sample many, many times. This is a case where we do not use probability axioms, the rules of probability. We don't use those regularities, right? We just use the law of large numbers. We pretend to sample many, 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 many times, and then we generate the probability distribution that way. We could do that. So you could flip a coin hundreds and hundreds of times, or you could use the probability principles to come up with a probability distribution. This one will take a lot longer than this one, but you know, you have to know more stuff in order to implement this. But these are also shortcuts, right? So that's nice. Well, in sampling distributions, you also have two different methods where you could come up with sampling distributions. One of these actually applies here, and that is this one. We could use law of large numbers and sample many times. Oops. Okay, so that's one way we could do it, right? Unfortunately, we can't use this one. There's no way we could use this one. But we can use something that we're going to learn about later called the central limit theorem. But for today, we are going to focus in on this one, using the law of large numbers to sample many, many times. All right. So before we go on to actually nitty-gritty generating these sampling distributions, here's how sampling distributions connects with the concepts of sampling, right? Remember, unbiased sampling, and research methods. Remember, experimental methodology versus those other methodologies? All right. So the promise before was this. If you use random sampling, right? And by random sampling, I mean unbiased, right? And if you use experimental design, we promised that you could draw sound conclusions about causation, right? We promised that that was the case. Now, in order to do this mathematically, right, in order to, because this has all been like ideas so far, right? In order to do this mathematically, sampling distribution is sort of the engine that allows this promise to come true. Because here's what the sampling distribution does. Imagine repeating your unbiased sampling and great experimental methodology over and over and over again, like millions of times, right? What kind of distribution would you see, right? So let's say you have this great experiment that you really want to do to see if, X changes Y, right? What would happen if we did that experiment over and over and over again? Over time, you would see the truth, right? You would see what might really emerge from that experiment. And that's how sampling distributions is going to help us reap the fruits of this promise. So without sampling distributions, this promise cannot fully come true.